Have you ever wanted to turn pure, abstract math into art? It might sound incredibly complicated, but you're about to see how just a few simple commands in a program like Mathematica can literally bring equations to life in beautiful, visual ways. Let's dive in and see how it's done.
All right, so here's the game plan. We're going to start with the absolute basics, just simple 2D plots. Then we'll level up to building 3D surfaces. From there, we'll check out a different way to think about shapes with something called contour plots, and we'll wrap things up by unleashing some serious creative power with parametric curves and surfaces. Let's get started.
First up, let's start with something we all recognize, a basic 2D graph.
So, for our first challenge, we're going to keep it simple. We want to visualize one of the most fundamental waves in all of math and science, the good old sine wave. And we're just going to look at one complete cycle, from 0 all the way to 2 pi.
Now, you might be thinking you need some long, complicated chunk of code for this, right? Nope. It's literally this one single line. You just use the plot command, tell it what you want to plot, in this case sin of x, and then you tell it the range for x, from 0 to 2 pi. That's it. It's that easy. And boom, just like that, we get a perfect classic sine wave. You can see it starts at 0, goes up to 1, down to -1, and finishes its cycle right at 2 pi. This is the core idea we're going to build on. Simple commands, elegant results. Okay, so we've got 2D lines down. What's next? Well, let's add a whole other dimension and start building some surfaces. So how in the world do we even create a surface? Well, instead of a function where y just depends on x, we now have a function where a height, let's call it z, depends on both an x and a y position. The best way to think about it is like a landscape, For every point on a map, there's a specific elevation. And the command for this is exactly what you'd probably guess. Instead of plot, we just use plot3D. We give it a function that uses both x and y, and then we have to specify the range for both variables. Here, we're plotting a classic bell curve, running from -2 to 2 on both the x and y axes. And look at that. That one single line of code gives us this gorgeous, smooth, bell-shaped surface. We've just jumped from a flat 2D wave to a full-on 3D landscape. This really shows you the power you get by adding just one more variable to the mix. All right, let's switch gears a little. So far, our functions have been pretty direct. But what happens when a shape isn't defined by a simple y equals f of x, but more like a rule? This leads us to a new way of plotting, and honestly, a super common trap for beginners.
This is what we call an implicit function. The absolute classic example is the equation for a circle, x squared plus y squared equals 1. See how y isn't spelled out on its own? The equation just gives us the relationship, the rule that any point x, y has to follow to be on that circle. Now, to plot these kinds of things, we need a different command. It's called contour plot. So let's try it with the equation for an ellipse, which is x squared plus 4y squared equals 1. We run the command and, well, Mathematica gives us this plot. But something seems a little off here. But hold on, wait a minute, take a good look at that. Does that look like an ellipse to you? No way. That is a perfect circle. We know from the math that it's supposed to be an ellipse, kind of stretched out. So what gives? Why is the picture lying to us?
Aha! Here is the secret, a real pro tip. The problem is that by default, the program just kind of crams the plot into a standard square frame, and that totally distorts the proportions. The fix is this simple but super powerful option. Aspect ratio automatic. This just tells the program, hey, make the axes scale correctly. And check it out. We add that one little option, and bam, the true shape just snaps right into place. Now we can clearly see the ellipse we were expecting all along. It's a fantastic reminder that sometimes you have to tell your tools how to show you the truth.
But wait, there's more. This contour plot command has another super useful trick up its sleeve. It can actually take a 3D surface and create a 2D map of it. Remember that beautiful 3D bell curve we made earlier? Well, there it is on the left. And on the right, that's its contour plot. It's like you're a drone flying right over the top of that mountain. Each one of those rings represents a line of constant elevation, just like you'd see on a hiking map. It's a brilliant way to squash 3D info down onto a 2D plane. All right, now we're getting into some really powerful stuff. What if you want to draw a curve that loops and crosses over itself? A standard function can't do that. For this, we need a totally new approach. It's basically like drawing with math. This is where parametric curves are an absolute game changer. The best way to think about it is like this. Imagine a pen moving across a page. At any given moment in time, let's call it t, that pen has an x-coordinate and a y-coordinate. And as t moves forward, both of those coordinates change according to some rule. By defining those rules, we can trace out all sorts of crazy paths.
And using the parametric plot command, we can generate these wild, intricate shapes. A curve like this one would be totally impossible to describe as a simple function of x, but with parametric equations, it's actually pretty easy. This just opens up a whole new world of creative freedom. Okay, time for the grand finale. We're going to combine the idea of 3D surfaces with the power of those parametric equations to build some truly mind-blowing objects. So if a parametric curve used one variable, t, to define a path, a parametric surface uses two variables, we'll call them u and v, to define the x, y, and z coordinates. You can think of it like weaving a sheet of fabric in 3D space. By controlling u and v, we can bend and twist and shape that sheet into almost anything we can imagine. And with the parametric plot 3D command, well, you can create things like this, a perfect torus, or donut shape. And remember, this wasn't some 3D model we just loaded in. This shape was born directly from a set of equations that defined every single point on its surface. It's pure mathematics made visible. So there you have it. We've gone from a simple little wave all the way to a complex 3D torus, all by turning equations into art. It's this incredible blend of pure logic and creativity. And that just leaves one question. What will you visualize next?